AstronomyCast, episode 265 for Monday, May 14th, 2012. Arthur Eddington. Welcome to AstronomyCast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. My name is Fraser Kane. I'm the publisher of Universe Today, and with me is Dr. Pamela Gay, a professor at Southern Illinois University, Edwardsville. Hi, Pamela. How you doing?
I'm doing well. How are you doing, Fraser?
Doing good. Now, last week, we asked nicely for donations. And a bunch of you responded, and that was fantastic. And I think we're going to make this a two-parter where we ask you for donations again. Which is so if if AstronomyCast is important to you and you want to help contribute to the show, we've got sort of editing people, transcript people, education outreach. And we really need your help. So you can go to astrosphere.org, and there's a place to donate there. And also, actually, you can actually donate from within YouTube as well, right?
Yeah, there's a link on YouTube, and you can just go to astronomycast.com, and there's a donations link there. We've done everything we can to make it easy for you to donate. So donate via PayPal, either via the AstronomyCast website, the YouTube website, or the Astrosphere New Media website. Fraser and I do this for the love of, well, actually it's more because you love it and we're trying to respond to your love, but we do have Preston, who we torture with our audio goofs. We have Joe, who's helping to keep everything running. We have Nancy, who writes our show notes. We have Rome, who does all of our transcripts, and we want to feed our staff.
Yeah, and the reality is that, we try to just focus on creating the shows themselves. I mean, Pamela's so busy, and so if we have all this help, and that helps us get all the other stuff that makes the shows really valuable, and that way we can just focus our efforts on doing the recordings of the shows themselves. So it means a lot.
So thank you in advance.
Thank you very much.
Donations
Thank you.
Tax deductible in the United States where law allows.
Yeah, so there you go. It's a tax write-off. All right, well, let's get rolling. So we can thank Arthur Eddington for much of our current understanding of stars. He provided some of the breakthrough concepts that explain what's really going on there deep inside the hottest places in the universe. And sadly, the spacecraft associated with his name wasn't so successful. Well, this episode is going to be great. He's a fantastic scientist, one of my favorites, and yet we're breaking our trend, which is that we do these two-part episodes. I know, but normally we do scientist and the spacecraft that was named after them, and in this case we are going to do scientist and the spacecraft named after him, but this spacecraft doesn't warrant its own show. It's kind of a footnote. It's one of those failed. NASA sometimes breaks its own rules, and ESA unfortunately doesn't have this rule, and the rule is you give the spacecraft a really dumb name until it launches. So, for instance, you had GLAST, which I don't even remember what GLAST stood for other than Gamma Ray Large something Array
Telescope.
Survey Telescope or something, yeah.
Right. So GLAST was a really cool acronym. GLAST launched. They renamed GLAST Fermi. Fermi is a great name, commemorates a great scientist. And we've worked really hard to limit the scientists we discuss based on they've historically changed the world enough that they have a mission named after them. Well, one of the things that unfortunately happens is occasionally names get removed from the list of spacecrafts because they've been used and then their mission never launched. And this wasn't the scientist's fault. So we're going to commemorate and celebrate Eddington for being a cranky guy whose mission didn't get launched.
Yeah.
And it's not his fault.
It's not his fault. We'll provide a little more information about that by the end of the show, but why don't we kind of go back around and then talk about Arthur Eddington. So who was Arthur Eddington?
He was a British scientist at the turn of the last century. He had an interesting upbringing. His father died when he was quite young, and he ended up pretty much being raised by his mother and sister and self-educated at home for a while. Eventually ended up going to school, getting scholarships to go to college, studied the sciences, eventually got scholarships, studied physics, went on, got his PhD. And throughout all of his upbringing, he was raised very much with a Quaker pacifist upbringing. And the reason I bring this up is because as a Quaker, he on one hand was a conscientious objector to World War I and escaped serving in any of the different ways they had scientists serving in World War I in Great Britain. But at the same time, as a pacifist, he is known for his academic arguments with folks. And so there's this wonderful juxtapositioning of conscientious objector to World War I, which I'm totally fine with, but also being the guy who got into these huge debates in the literature over how stars are supported or not, depending on who he was arguing with.
And so he was one of those people that just couldn't let an argument go?
No.
I mean, you know the type, right?
I do. I've worked with the type.
I might be that
no, science is filled with them. There's different debates that you know won't end until the dude dies. And unfortunately with Eddington, he was the dude that we had to wait die.
So he had a cranky, cantankerous personality. He would argue to the death about the things that he believed in, but at the same time didn't want to pick up a gun. I can dig that. I'm totally fine with that. I like. So then what was his background?
He was a scientist who had a very, very strong mathematical background, and not all astronomers are strong mathematicians. Some are very good observationalists, some are very good with computer science. I tend to be on those two sides. But he was amazing with both the mathematics, and he could also do observations when he needed to. So he really started to make a name for himself in how he looked at stars and the ability of stars to support themselves, because he went from looking at their Cepheid pulsating variable stars, and the fact that they're pulsating was kind of a new and novel idea when Eddington was doing his work at the beginning of the 1900s. And he was trying to figure out, how do you get giant luminous stars that vary in brightness? And the idea of them being binary stars was something that kept coming up over and over and over again. But when he looked at, well, how big would the orbit have to be to make everything make sense, he realized that the stars had to be bigger than the orbit of the binary, and you can't end up with a star causing an eclipsing binary if it's orbiting inside the star it just didn't work. So he came up with the notion, well, maybe stars are supported in a way we haven't thought about before. And it's kind of hard to imagine, but when he was working in the early 1900s, we hadn't figured out how stars worked yet. People were still considering, well, are they supported via heat? Is it simply the ideal gas law and they're hot due to some sort of chemical burning? And so everything was using the ideal gas law, and that was kind of the right track, but the notion that light pressure, radiation pressure played a role wasn't there. The idea that it wasn't chemical burning, it was nuclear burning that was going on was an idea that didn't even exist. And
so in other words, so before Eddington had a deep think about it, they actually thought there was some kind of chemical reaction going on inside stars?
People actually did calculations on the basis of, well, what if stars were made of coal? How long would they last? And other similar chemical ideas. Yeah, it was basically along those lines of, let's imagine if stars were composed of the most efficient fuels known at the time, and different people did all sorts of different calculations, and you couldn't get stars that lasted nearly long enough to even match. Big
ball of gasoline, yeah.
Yeah, and they couldn't match the geological record. Stars were all far too young. It was very confusing. And then the whole idea now of pulsating stars, couldn't make any sense out of that one. And so Eddington came along, and he added in the idea of radiation pressure. And without having a physical explanation for the radiation pressure, he started devising from first principles ways of looking at how the different forces have to balance one another to have gravity crushing in and radiation pushing outwards to balance the star. And he got equations that worked. He could model stars. He could explain the relationships between mass and luminosity. And he had no physical explanation for it. It was this beautiful work, sort of along the lines of what Kepler did with planetary orbits many centuries earlier, where there was a problem, there was observation, and he matched the observation, and then it took others to come along and explain the physics.
Right, so he knew he could come up with an idea that matched what he was seeing, but they still had no idea what would be causing such a thing.
Yeah.
Now, but I mean, this concept of radiation and pressure, I mean, there was a lot of work being done on quantum physics, on relativity, all at that time. So it was, a lot of that must have been starting to inform his thinking.
It was informing his thinking, and what's really interesting is a lot of what he did initially started off with him and Russell of the HR diagram, basically debating how these giant stars supported themselves, trying to explain the velocities seen in the spectral lines. And it was out of his conversations with Russell that he was able to develop his theories, and Russell would say, "But did you think of?" And Eddington would absorb these ideas until his theories really started to be able to match what was being observed. And what was kind of awesome is as Eddington thought through the quantum mechanics and thought through how light and matter interact with one another, he started to take into account things like, well, maybe part of what's able to drive these pulsating variable stars is changing opacities in the outside of the star. And so even while they still didn't fully understand nuclear fission and fusion, he was able to start thinking through things like, well, maybe if you change the opacity in the outside of the star so that suddenly the light can't push through the outer atmosphere, you'll be able to build up energy, and this can drive the pulsation by changing the opacity. So Eddington was actually one of the first people to figure out, how do you make stars pulsate? He was one of the first people to develop working models for the atmospheres of stars. And he was actually the one that Chandrasekhar worked with while he was doing his early research. And that's where the ironies start to crop in.
Right, and so you can imagine this understanding, right, that light is pushing out from the interior of the star, and it's hitting this, I guess, this opaque layer, and then that's almost billowing it out like a balloon, and then the opacity is changing, and it's almost like it's releasing that light is now able to escape, and it sort of, I mean, it changes it would even change the size and shape of the star dramatically in a very short period of time, and then it would build back up again, right?
And so what actually ends up happening is you have these large stars, and as they expand out, they cool. And they eventually get large enough and cool enough that the helium atoms, or whichever atoms are responsible in a given star, deionize. So they reach out and they grab all of their electrons, and when they grab all of their electrons, they suddenly become more opaque. So this changes the opacity of the star, and the way it works is when it gets too big, it becomes more transparent. It's able to collapse down. When it collapses back down, it heats up, it ionizes, traps the energy again until that gives it a kick. And part of the kick that it gets is that moment when the helium ionizes, there's extra energy released in that process. Or it's the interplay between when things are ionized and when things aren't ionized that's causing this extra kick.
I've got an analogy. You know, if you ever taken a hair dryer and you put a ping pong ball on top of it, you turn on the hair dryer and the ping pong ball kind of floats up in front of it, and then you turn off the hair dryer and the ping pong ball falls down, and then you turn it back on and it floats back up. But the point is that it's hitting that balance point between the thrust of the air from the dryer and gravity pulling it back down. And then you turn that source of thrust off, and then boom, the ping pong ball will drop again.
This is a lot more like one of those little bobbing birds that you can get at science museums.
Yeah, it's drinking the water.
It's drinking the water, and eventually it gets enough stuff in it that it changes, empties, bobs forward, and it's much more similar to that bobbing bird. Yeah.
So, but let's go back to Eddington here, because I think we're getting too off course here with the science. Right. So he had come up with this idea. How was this idea received by the scientific community?
Over time, it was gradually accepted. Initially, it was problematic because he put forward an idea that there was really no physics to support. There was just a lot of light pressure supporting stars and nothing supporting the light pressure. But over time, as he was able to incorporate in people's arguments, as he was able to say, well, what about this, as he was able to reproduce the mass-luminosity relationships that we're seeing, and as people figured out fusion and fission in stars, as all of these things came together throughout all of the development of astrophysics, because this was the time when astronomy started to split, so that we had people that were doing just plain observational astronomy, which is awesome, but we're also delving into the astrophysics and explaining the hows and whats that was driving all of the things that were being observed. As all of the astrophysics developed, his theories gained detail, gained prominence, and are now part of how we understand how stars work.
And so he was working on this, and I guess this is where he gained his reputation for being a bit of a crank, or not a crank in the sort of scientific way, but a cranky. He was a debater, right? And so he had a fairly famous relationship with Chandrasekhar.
Well, and Jeans as well, and it was Jeans. So here's the funny part: we have Jeans, who's the another big pillar of astrophysics at the time. He was one of the ones that helped define how gas clouds collapse to form stars, the Jeans instability, and so many other wonderful things in gas laws. And Jeans was just like, no, you do not have a physical basis for what you're saying. And so the two of them had this fabulous debate going on in the literature that boiled down to Eddington saying, but it works, and Jean saying, right, but you don't have a basis. And,
right, that's a fantastic theory, but we all know that coal can't generate that amount of light pressure, right?
It wasn't quite that, but yeah, it was along those lines.
Yeah.
And so it started with, you have you have Eddington versus Jeans going back and forth. And then poor Chandra was a student. He was brilliant, probably one of the most brilliant scientists of his age, and it's a pity that Einstein so overshadowed him in the public, because Chandrasekhar really could have been an amazing role model as well. Chandra, on the way to England to go to graduate school, pretty much sorted out that when stars begin to run out of nuclear fuel, this is working later on after people have begun to understand the nuclear processes inside of stars. When they run out of fuel to generate the light pressure to support the outer parts of the star collapses. When star collapses, you end up with everything under vast amounts of pressure. And as he ran through the math, he realized that there's a certain point where what's left, that white dwarf star that's created when a sun-type star collapses, the electrons in the star are packed so closely together that they no longer act like a normal gas. They, in fact, become what's called an electron degenerate gas, a relativistically degenerate gas. Suddenly the Pauli exclusion principle no longer applies in the same way. All the things you learn in first-year chemistry go out the window. Math becomes both much harder to understand and much easier to do. And he realized all of this on the boat. And then he realized while he's on his way to graduate school that at a certain mass, that electron degenerate gas is no longer able to support itself anymore. And in fact, something needs to happen. And this led to the ideas of neutron stars. This led to the ideas of black holes. All of these things derived out of this notion that when gas is put under a certain pressure, it just sort of goes no. And something has to radically change.
But without that light pressure is really the key, right? It's that light pressure is the thing that's holding the whole thing together. And if you get it to the right state, then you're going to lose that light pressure, and then the whole thing is going to collapse inward. So Chandrasekhar comes with, fresh off the boat with a head full of really challenging ideas,
And Eddington goes, no.
And Eddington says no, which is kind of weird because he had, had just recently been delivering a whole bunch of really challenging ideas to a scientific community that said no.
And so this is one of those things that I look at, and it's one of these moments of a scientist being a human being, where poor Chandra, he spent night after night after night talking about his theories with this advisor, with this colleague, and goes to present at a conference, gets to the conference, sees when he gets to the conference that Eddington is speaking on the same topic he is, the topic of what happens to stars when they no longer have light pressure supporting them. And Eddington basically gets up, the man Chandra's been discussing all of his ideas with. Eddington basically gets there and stands up and does what half the cranks in my inbox does and says, who can believe this theory? It makes no sense. What is it, that stars are just going to collapse down until gravity prevents light from
some
flying
kind
away?
Of dark matter? Or
dark stars.
I don't like it. The scientific argument is very compelling. Yeah.
So Eddington basically makes the argument of black holes make my stomach unhappy, therefore they can't exist, which isn't valid.
No.
And so it's this matter of genes, and Eddington had this debate where genes was going, you don't have a physical underlying theory, dude. And Eddington continued on until it worked and everyone respected him. Then Chandra comes along and says, I have a theory based on physics. And Eddington goes, it doesn't make sense. Who can believe in those objects existing? And
Now I know that Eddington was a big fan of Einstein too,
yes.
Right?
Yes, and that was one of the interesting things that also came out of him being a Quaker in some ways, is during World War I, when he looked around the community, he made the choice to try and keep science going, to keep the international community moving forward, even in these times of war. And it's wonderful to look at the various people who've done this during both World War I and World War II. And during World War I, he was one of the people that looked around and saw this theory being developed by a young German and called attention to it. And because he was such a superb mathematician, he had the ability to really get a lot of insight out of what relativity had to offer. And so over the next, actually decades, Eddington was one of the people working very hard to popularize relativity and to make it something that people who didn't have his mathematical abilities were actually able to comprehend. And Eddington actually worked really hard to not just communicate it, but to also prove it, and led an expedition to take photos of the 1919 eclipse of the sun to see if he could measure how the light from the stars got bent as it passed near the sun, to see if the bending reflected strictly Newtonian gravity or both Newtonian gravity and the predictions of general relativity.
And what was the result of the experiment? I know there was a great TV show. Did you see that?
No, I didn't.
It was like a movie. It was called Eddington and Einstein and Eddington. And it sort of details the whole story and their sort of letters back and forth and the work that Eddington did that helped really validate Einstein's discoveries.
Well, and the funny part is that Eddington's observations weren't that great. There was actually a second team that made observations that seemed to rule out relativity, but they had mechanical issues with their telescope. So Eddington just sort of ignored what they did and read a lot into his poor observations, and the world was more than willing to accept relativity based on this bad set of data that mostly mostly showed that relativity worked. But since then, there's lots and lots and lots of evidence taken with better telescopes and we fully trust relativity. It's just funny that the world accepted it based on kind of bad data.
But would you say that Eddington's vote of confidence for the theory really helped propel Einstein as the science rock star that he became later on?
Well, I think the rock star had more to do with the fact that Einstein did have such a unique haircut and personality.
Okay. Right, but the point being that his ideas were deeply challenging to the established status quo, and yet to have such a prominent scientist in England be able to provide that level of commitment to stand behind it meant a lot to help Einstein's career path, and helped him with some of his future, where he ended up in the United States and things like that.
No, that's entirely true. And in fact, in a way, Eddington helped popularize Einstein and also helped motivate Chandra to be an amazing researcher through basically making it impossible for Chandra to advance his career goals in England, and making it such that everyone knew about the work of this young German scientist. And so that young German scientist, Einstein, was able to get jobs in America, escape Germany, and have a fabulous career. And Chandra realized, I'm never going to have a career in England. Got himself out of Dodge, went to Chicago, and built an amazing career there. So two completely different ways of motivating someone to switch universities, and Eddington was responsible in many ways for both of their different careers.
So as some of the other thinking, like fusion, the ideas of fusion power in the star, how did that inform his thinking? When did those?
Well, so that all started to come in piecemeal. So he was developing his theories based in a lot of cases just on dimensional analysis. So any of you who've taken a physics class and had your teacher yell at you, did you check your units? Eddington actually started with the units. He started figuring out, okay, so how do I balance this, that, and the other forces together to get everything balanced to balance the star? And he identified the empty pieces, and then the rest of the scientific community luckily advanced and helped fill in those empty pieces. So it all came together. It was an awesome time, and it's hard to tell without dedicating a year to researching this how all the pieces came together specifically.
He had a lot of pretty interesting philosophical ideas as well. I mean, he was not only a very skilled researcher and really pushed the concept, the solar physics idea ahead, but he actually had a lot of fairly interesting philosophical, he was an idealist. Had a lot of his arguments came from that as well. How do you think all of that sort of played into his concepts of, his concept, his cosmology, and sort of his ideas on physics and astronomy and things like that?
I think in a way it led him down a very strange path in the end of his career, where he started trying to build, like so many scientists in the time did, a theory of everything. But for him, his theory of everything was actually numerology.
But I mean, I was, in researching this show as well, it was really interesting to me that it's almost like when you begin your research into your theory of everything, that's when you're about to die. That's when your career ends, and that's sort of the thing that will end everyone's lives, Like Einstein was doing the same thing. And so you look at and researcher after researcher, and then, nearing the end of his years, he investigated the possibility of a theory of everything, incorporating,
and now we mock him for what he looked at.
And now we mock him for what he looked at, Although, there's a certain amount of mockery even reserved for Einstein.
No, Einstein was determined that quantum was a bad thing.
So all I'm suggesting is that there are any researchers out there considering working on the theory of everything, be careful, because it just might kill you. It's the cursed theory. That's just my theory. That's what I'm thinking right now.
No, it's just really strange, the path that Eddington's career took towards the end, because he was working really hard to try and figure out numbers and how they factored together, where he assumed that the numbers associated with electrons and protons had to be written into the firmament of the universe, and that there was something special in the 1 over, at the time, it was originally thought to be 136 of the fine structure constant, and then when it was realized it was closer to 1 over 137, he was like, oh, no, this actually totally makes sense now. And
that makes sense. Oh, yeah.
And it's just kind of sad to watch. I don't know.
Yeah. All right. Well, I think so. I guess we're going to wrap up. So where did he die?
In England.
Yeah.
Yeah. He lived a good life. He passed away towards the end of World War II. So he lived during that amazing time in England where the country saw all manner of horror, all manner of political change, all manner of social change. He passed away in 1948, having started his career at the beginning of World War I, really as a professor, and it was an amazing time to be alive, especially where he was alive, and he really helped define our field, and almost got to define the name of a mission, but they didn't launch it.
Right, and so this is. And so what happened with the mission? What was the mission supposed to do?
It was supposed to search for Earth-like planets.
Oh,
yeah,
that would have been awesome.
It would have.
Right.
It's a mission that's canceled. It was going to be very similar to the Kepler mission. It was going to observe about 200,000 stars, look for changes in light due to the transits. It just never got built. So.
And they made that terrible mistake of naming it before they launched it, and so now the Eddington name is lost forever.
Yeah. Well,
really?
Who knows? Really, I don't know if it's forever. I don't know what I don't know what the superstitions about sharing names is, but right now, ESA lists Eddington as canceled.
Right. Somebody should. Well, I still think there's going to be a need to build a mission of almost that exact profile, especially when you look at the success that Kepler's been having in discovering planets. Yeah. To build another spacecraft right on the heels of that and focus more on Earth-sized planets, I think it would be awesome. So I think that's great. Have you ever heard of the Eddington number for cycling?
Yes.
Because that's big in the cycling community.
Painful. Oh, so it's the number of days that you've done more than X of what you've done before. It's the number of consecutive days that you've done a ride of a distance. So, in other words, if you say you have an Eddington number of 5, it means for the last 5 days you've ridden 5 miles. Okay.
And then 6 is the last days for 6 miles, and so if you get to 70, then you've had 70 consecutive days. You've done 70-mile rides for 70 days, right?
And
the
it
number,
has to be consecutive?
It might not be consecutive, but it's the number of days that you've cycled for more than a certain distance. And so the point being that the higher that number gets, the more difficult it is, because it's the number of, because, to get 70 miles, to continuously hit 70 miles is brutal. So, but he was a real avid cycler, though, right?
There's actually, and what's interesting, there's a related number that we use to determine which professors are leading researchers and which aren't, and that's what's called the H index, and it's how many papers have you had that have been cited by more than X people.
Oh, right. And so the bigger that number is, the more meaningful it is.
Yeah.
It's almost like it's an exponential or logarithmic.
Yeah.
Yeah, progression. That's really cool. All right. Well, thank you very much, Pamela. That was great. And
my pleasure, Arthur. Okay, stopping the recording and saving the recording. And we're not really going to be able to take questions today, I'm afraid.
No? You're too busy? Okay.
Well, I have a 3 o'clock meeting, and it's 2:59.
Okay. No problem. Let me see. I don't think we got a lot of questions anyway. It's not consecutive, so no. Not consecutive days.
Okay.
Do you still have time to do research? Yes, you're going to go do research right now.
Yes, that's why I have a meeting.
Yeah, that's fantastic. Yeah, Einstein and Eddington. That's right. Yeah, it was David Tennant played Eddington.
That's
It was fantastic. Yeah, it's awesome. It's really good. I really enjoyed
We'll
it.
have
So
to
I
find
highly
it and
recommend.
link to it in the show notes.
I think it's on. I think I watched it on Netflix.
Okay.
Yeah.
That's cool. I'll
Yeah.
have to go look.
Cool. All right. Well, thanks. Sorry we can't stick around for questions. Thank you very much, Pamela. And we'll probably be recording Monday. If anyone wants, we're going to be doing our virtual star party on Sunday night at about 9 o'clock Pacific time when it gets dark on the West Coast, and we'll hook up a bunch of telescopes into a Google Plus Hangout and show you the night sky. And actually, I think we're going to have some. Hopefully, we'll have the Moon, Saturn, Mars
coming up.
And then a bunch of and all the nice summer objects are coming up. So last week we had the Ring Nebula, we had the Columbia Cluster and Hercules. So it's getting to be one of my favorite times of the year to do observations. So I hope you guys can join us. That's right here on Google Plus. All right. Well, thanks, Pamela.
Okay.
I'll let you get to your meeting. Thanks everybody for watching, and we'll see you all next time.
Okay. Bye bye.